gives me a great pleasure to welcome you all here and to introduce tonight's speaker. But before I do that, I wanted to say a few words about what this event is all about, kind of put it in a broader context. And for some of you, it may be repetitive, certainly for the students in the audience, they know all about this event, or if you've been here to previous summer school lectures. So this event is brought to you as part of the so-called Boulder Summer School for Condensed Matter Materials Physics. This is kind of an advanced study institute that takes place on Boulder campus every July for 4 weeks. We invite 65 talented, most talented students from all over the world to come and spend 4 weeks here and to learn about recent frontiers in theoretical physics. And they're lectured to by 20 to 25 experts in the field of the school. So in the past, the school has been in existence for 17 years, so this is the 17th school. It started in 2000, and our speaker was actually one of the first lecturers in the 2000 school. The schools have ranged on many topics, all the way from something like superconductivity to magnetism to biophysics. So it really covers a broad range of topics, and they vary every year. So every year there's a new class of students, there's a new set of lecturers that come and lecture here. The school is supported by valuable funds from National Science Foundation and also locally from the University of Colorado the Physics Department. And so these are you're seeing your tax dollars at work here, and particularly this lecture. This year's school is on topological states of matter, which is not that easy to define. In fact, part of the school is to discuss what exactly that is. And part of today's lecture, you will hear kind of a glimpse of what it is all about. One thing I will say is that it's definitely, we can probably all agree on, it involves quantum mechanics at a macroscopic scale. So that's an essential ingredient, as you will hear tonight. So turning to tonight's lecture, our lecturer is Leon Balents, professor at the University of California, Santa Barbara. Leon was an undergraduate at MIT, and then he moved all the way across, one train stop across to Harvard, where he got his PhD in 1993. We were actually classmates there, so it was a real pleasure to interact with him for 5 years and had a relationship since then. After a brief stint at Bell Labs, a few years, Leon moved to UCSB, where he has been a professor since. Leon is well known for his studies of quantum matter, but actually also soft matter and disordered systems. It's probably easier for me to name things that Leon does not work on than things that he works on. And certainly members of the school who know him for his physics will second that. He's a really prolific writer and very clear, has a very clear way of describing physics, very complicated physical concepts, as you will hear tonight. So tonight he will tell you about second quantum revolution, to be contrasted with the first quantum revolution that came at the turn of the 20th century. And so he will tell you what that second quantum revolution is. So without further ado, please join me in welcoming Leon.
Thanks so much, Leo. It is really a pleasure to be back here and also to follow up your excellent lecture here. This is my third time here for the Boulder Summer School, and it's always been really fantastic. Let me get on. This is my father. He passed away 4 weeks ago, so I would like to dedicate this to him. He is one of a major influence in getting me into physics. I was back at my parents' house at that time, and I came across this book, The Dancing Wu-Li Masters. She gave to me at that time. It's a book combining quantum mechanics with Eastern philosophy. And it really inspired me to get interested in quantum physics and want to learn that. And so this talk will be about quantum physics without the Eastern philosophy, because I've forgotten whatever I learned from that book. And it'll be sort of in two parts. The first part will be kind of a review. I'm sure many of you don't know much about quantum physics, what's quantum physics about, some of the key points, and then I want to turn to this recent revolution in our understanding of how to bring quantum mechanics to our macroscopic world and make it visible. So to tell you about quantum physics, I need to explain what happened before. For most of us physicists, we say that the story of modern physics began in 1687 when Isaac Newton wrote his famous Principia, where he laid down what are now the laws of classical, we call classical physics or Newtonian physics. So Newton taught us how to describe motion with mathematics and introduced some simple physical laws that would describe this motion, like the motion of a tennis ball. This is the equation for the height of the tennis ball as a function of time. So if you hated freshman physics, this is what you learned in freshman physics, you should blame Newton. Okay. On the other hand, if your homework looked like this, then you rest assured that your instructors hated you too. So Newtonian physics is extremely useful. It allows us to design skyscrapers and bridges, to build better skis, which must be important here in Boulder, and describe the motion of the planets. It even sometimes lets us predict weather, although we all know that doesn't work all that well. So it has worked amazingly well for hundreds of years, but it turns out it's not quite correct. By the beginning of the 20th century, more and more evidence had piled up that Newtonian physics did not work for very small things like atoms or electrons. For example, the discrete emission lines of hydrogen, as shown in the middle there, or the spectrum of black body radiation, the different colors that come out of an object when you heat it up. These are not described by classical physics. Many, many more things had piled up by around that time. And driven by these and other observations, physicists developed quantum mechanics. Quantum mechanics is amazing. And it's hard to really say why it's amazing better than did the noted physicist Sheldon Cooper. So I hope we're going to hear this.
Quantum physics makes me so happy. Like looking at the universe naked.
So, I really couldn't say it better. I'm sure all the students feel like this. So quantum mechanics is probably the most successful theory of physics. It's almost something we shouldn't call a theory. It works. But it's extraordinarily strange. So I'll try to introduce you now to two of the cornerstones of quantum mechanics. These are the concepts of superposition and of entanglement. So superposition first. So I mentioned quantum physics becomes necessary for small objects. So I'm going to, during this talk, largely talk about some of the smallest objects, and I'll use the state of a single electron as an illustration. So it's a pretty important one. An electron has a property known as spin. That spin could be up, or that spin could be down. Equivalently, you could think of the electron as spinning clockwise or counterclockwise. But quantum mechanics is very weird. If two things are possible, then both of them are possible. So the electron doesn't need to be up or down, it could be both. You can add those things. When we add two things that seem real to us, we're doing what's called quantum superposition. A physicist usually likes to represent the state of a system, this kind of superposition, by a wave function. We call it a wave function, and we use the letter psi a lot. The Greek letter psi. So in quantum mechanics, we can add states with any coefficients. You can multiply them by numbers. So we can put numbers in front of these states. We call them amplitudes. So you notice the spin is not up or it's down. It's neither of them. The upness or the downness of the spin is not the thing which is real. The real information in the quantum mechanics, the thing which is real, this wave function is real, is the information in the coefficients. It's these amplitudes. We call it coefficients amplitudes. So in a way, and it's kind of natural to regard the information as what is reality in quantum mechanics. The more and more that's becoming the point of view of modern physics. The reality is information. So if we think of one of these spins, it has two classical states, so it's like a bit. It's like the bits that your computers or your cell phones are based on. It could be up or down, like a 0 or a 1. But a quantum bit is different. It can be a superposition of those. So you can think about it as taking states in between up or down. We could draw it pictorially by letting our arrow point in different directions. So what does it mean physically? Well, we should think about an experiment. So it's possible to make a machine that will take an upspin, stick it in the machine, and it will come out as a superposition, of equal superposition of up and down. So it means it's neither up nor down, but as much up as down. So that machine has a name. It's called a Hadamard gate. And now we can do an experiment. We can take this spin, which has been superimposed in up and down, and we can give it to a second machine to measure it. I call that machine a graduate student. He's in the audience, actually. So our student measures a spin, and he finds it to be up or down, one or the other, not both. It's impossible to predict which, but if he repeats the experiment many times, each time the result is random, up or down, and they come with equal frequency. You'll get a lot of ups, lots of downs. After that, if he were to measure the same spin again, if it was up before, it stays up. So this is called the collapse of the wave function. After measuring this spin, we know its state, and it's no longer a superposition. So this is called the Copenhagen interpretation of quantum mechanics, and we'll come back to this active measurement, which is kind of mysterious in quantum mechanics. So our graduate student is suspicious. He's wondering if this thing is really working. I mean, after all, he always sees an up or a down spin. How does he know he actually got a superposition? So he's suspicious. He thinks that maybe this is not a quantum machine, maybe it's a classical machine, and there's just somebody inside there flipping a coin, and if it's up or heads or tails, he spits out an up or a down spin. Maybe there's never any superposition. So our student is pretty clever. He devises a test. He says, well, let me take the spin that comes out of this machine and not measure it, but just stick it into the machine again. Okay. And at the end, sees what comes out. So if this is just a classical machine, some guy flipping a coin up and down, it's going to come out equally up or down. And then he does the experiment with the real Hadamard gate, and that's not what happens at all. Actually, it always comes out down. So that's quantum weirdness for you. A very simple-minded explanation is you can have, if you think about the spin, these superpositions as just rotating the vector. The machine rotates it once, then it rotates it again, and it comes out down. So that's superposition. Things can be in two or more states at once. In a way, the second ingredient in quantum mechanics, this quantum entanglement, is even stranger. So to talk about entanglement, we need at least two objects, two spins. So, and we have two people, Alice and Bob. It's always Alice and Bob in these talks. You've been to physics talks about this. Always Alice and Bob. So Alice has a spin and Bob has a spin. And they could both be up, for example, or they could both be down. Now in quantum mechanics, of course, we can use superposition, and it applies just as well to these two spins as to one. So they can have spins that are both up and both down. Now in quantum mechanics, Alice and Bob can be very far away from each other. One of them could be in South America, one of them could be in Africa. This is the basis of a very famous thought experiment by Einstein, Podolsky, and Rosen. It's called an EPR pair. It's something very strange. It's strange because the state of either one of the spins is completely undetermined. It's as likely that the spin Alice has is up or down. It's completely random, actually. And the state of Bob's spin is equally unknown. But the state of the full system is not. It's completely determined. And for example, whatever spin Bob has, it's the same as what Alice has. So what bothered Einstein about this, really all his life, is that the state of the system, you can ask, where is the information that the two spins are pointing the same way? Where in space is it? Well, it's not in any specific location. It's not where Alice is. It's not where Bob is. We don't really know where it is. In quantum mechanics, the information of the state of a system doesn't have any definite location. So this is sometimes called quantum non-locality. And this phenomena that we have two quantum mechanical objects where a measurement of one, where information about one determines the property of another, is called quantum entanglement. So there are experiments that prove that this is actually the case. This really is the way the world works, that there is no real sense, there's no sense in which reality is stored locally in the world. The seminal experiment was devised, the idea was devised by John Bell, came up with what's known as Bell's inequality, and it was tested to high accuracy with experiments with photons. This curve here is the prediction of the theory of quantum mechanics, and what Bell proved is that any result, anytime this curve lies in the hash regions above or below, and those dots there are experimental data, that means there can be no local reality. So the real world around us is very, very strange. So in fact, an entangled pair is so different from anything classical, it can be used practically. Probably the most famous application is it can be used in a field which is called quantum cryptography. You can use this sharing of information as a way to transmit keys like you do when you use a secure connection on your internet browser, you use RSA encryption. You can transmit those keys 100% securely, with no way that you can be overseen by any malicious power or government. This is a real thing. There are at least 4 companies that are actually marketing these systems. Now we come back to measurement. Measurement is strange. If Alice were to measure her spin, as I said, it's completely undetermined. And so Alice will randomly measure the spin to be up or down. However, the instant Alice makes that measurement and finds that her spin is up, she knows that Bob's spin is also up. As far as we know, there is no limit to the speed at which that occurs. Okay. So that is something Einstein didn't like. He called it spookhafte Fernwirkung, which means spooky action at a distance. But this is the one instance in which Einstein's intuition really failed him. He didn't believe quantum mechanics could really work like this. The world could really work like this. But, these experiments by Bell and others, by Aspe actually, prove that it actually does. So I mentioned a couple of times just now and earlier this phenomena of collapse of the wave function. So this is a standard way you're taught quantum mechanics when you take quantum mechanics as a junior year of college. That when you measure something, afterwards the state becomes definite. The wave function collapses. So you can wonder, what actually constitutes an observer to carry out a measurement. You tend to think this is some kind of like a human element. Does the measuring device have to be a human that's conscious for the wave function to collapse? Or can just some piece of laboratory equipment do it? If it's a piece of equipment, we'd say, okay, we measure the spin, turns out up, and then both spins are up. So does that mean that our measuring device in the laboratory is conscious? My Latin may be wrong. Use Google. This is supposed to mean I measure, therefore I am. Well, it turns out that a literal collapse doesn't actually need to occur. Interestingly, entanglement, although it provides for us this weirdness of quantum mechanics, it also explains why it is that quantum mechanics doesn't appear to us when we go about our daily life in the macroscopic world. Entanglement itself leads to effects that are indistinguishable from collapse. So when our measuring device measures a spin, the device itself becomes entangled with the spin that we measure. And it turns out that you can show by just the theory of quantum mechanics that unless we can control the full quantum state of the system, which now includes our measuring device, it will appear as though the wave function has collapsed. And so this means for practical purposes, anything can be an observer. It doesn't need to be conscious. It could be another electron. It could be an air molecule. Anything around us. So entanglement is kind of a weird thing. It's a very quantum thing, but when it's uncontrolled, it makes the world appear classical. So uncontrolled entanglement is our enemy, what we really want to do is control entanglement and put it where we want it. So that's kind of my review of quantum mechanics. I want to go down and talk about more modern things. So we've been talking about electrons, tiny microscopic things. What about things we can actually see? You may not know it, but the matter around us, the things that we actually see, contain huge numbers of microscopic particles. Just a cubic centimeter of just about any stuff that you can get your hands on contains as many atoms in it as there are stars in the universe. So if we want to see quantum mechanics in a macroscopic piece of material, we're not talking about quantum mechanics of one particle or two, we're talking about quantum mechanics of that many particles. So there's a famous parable in quantum mechanics, which is called Schrödinger's cat. He devised, this is often discussed to bring to light the strangeness of quantum mechanics. They imagined a situation in which a cat could be put into a superposition of alive and dead. And I had to work rather hard on my daughter to get her to draw these pictures because she wasn't happy with the idea of a dead cat. And I said, the cat's not dead. And I wasn't lying. But please don't look too hard at it because you might measure it. So this is a very highly entangled state because it's actually the state of every atom in the cat, okay, which is more than the number of atoms I showed you on the previous slide. And all those have to be entangled with one another. So either way you want to think about entanglement, this kind of highly entangled state, Schrödinger cat state, if you want to think about it as something which collapses if we make a measurement of it, or something which is, because it has so many atoms in it, is liable to get entangled with other things in the environment, it's a highly unstable state. For example, any air molecule that randomly collides with the cat is going to collide differently with the live cat and the dead cat. And so the state of that air molecule gets entangled with some of the molecules of the cat. So because of that, entanglement with the environment, this is called decoherence. This uncontrolled entanglement with the environment, the Schrödinger cat is highly unstable. And you should never really expect us to be able to produce a real Schrödinger cat of a cat. People can actually make Schrödinger cats of a small number of quantum degrees of freedom, like photons. Even if we give up on making Schrödinger cats, we can ask a different question, which is how much entanglement of large things can be achieved? How much long-distance entanglement between many, many electrons or atoms, how much quantumness can we achieve in a macroscopic object? And we'd like it to be stable. We want it to not immediately go away due to decoherence, due to entanglement with the environment. That's a challenge. That's the billion-dollar question. How and how much such entanglement can we stably create? Kind of second question that occurs to you when you ask that is, how would you ever create such a thing? The reason that's a little bit subtle is that forces between objects, electrons for example, or atoms, they tend to be very local. The forces are much larger when something is close to one another. You see that, of course, in the macroscopic world. You have to touch something to push on it. Okay. So if most forces are local in nature, why would these quantum degrees of freedom arrange themselves in some way so that things that are far apart are entangled? Well, this is actually a question that arises not just in thinking about quantum mechanics, but in thinking about all types of things around us. Actually, we're surrounded by different types of matter that have extremely complex structures, like those of a snowflake, or the regular pattern of atoms in a solid, that's chromium. They arrange themselves in this incredibly ordered pattern, very, very far away from each other on atomic scales, even though the forces between them are very short range. So this is a phenomenon called emergence, and matter undergoes all sorts of complicated, beautiful types of organization. Usually in our field, condensed matter, we call different types of organization of matter phases of matter. This is the same sort of notion that when you probably learned in high school that water can be solid, liquid, or gas. These different patterns of organization of atoms, electrons, etc. Are phases, and you can get very, very many of them. Actually, the left-hand side here is a phase diagram of water as a function of temperature and pressure. And there are more phases than you might have thought that there are. Lots of different types of water. You start mixing up different metals, you get incredibly complicated phase diagrams. So there are actually many, many phases of matter. However, despite the fact that there are many, many phases of matter, not very many of them that we know of, occurring naturally anyway, have this kind of very strong quantumness about them. In fact, it turns out, this is a result that's become very well known in physics in the last decade, that most matter obeys what's known as an area law of entanglement. You can ask how much entanglement is there between stuff inside some region, here I draw region A, and stuff outside that region. And it turns out the amount of that entanglement is proportional to the area of the boundary. That's called the area law of entanglement. What it means, the way you can understand that, is that basically just spins or electrons, things that are near the boundary, are entangled with those on the other side. So most entanglement is like that. It's kind of short distance entanglement. There's lots of that in materials around us, actually, but it's not so useful. We want to be able to take advantage of long distance entanglement like that between Alice and Bob. So until recently, we probably thought that most matter only had short-range local entanglement, but it turns out it's not true. Matter can actually have non-local entanglement. So the genesis of this idea actually goes way back. As a physicist, we like to feel superior to chemists in all possible ways. We deride them constantly. But the original idea behind the modern incarnation of highly quantum phases comes from a chemist, Linus Pauling, who came up with the idea of resonance in chemistry. So on the right there is the chemical structure of benzene, one of the common molecules in the petroleum industry. It's carcinogenic, so you don't want to handle too much of it. One picture of the bonding of chemistry of benzene is that it's, as you go around the ring, which is carbon atoms, you have single bonds and double bonds. But Linus Pauling realized that you could have two choices of that bonding. You could put the double bonds between the even atoms and the odd atoms. And he said he explained that those two structures would resonate between one another, and that's often drawn as the bottom picture there. He called this resonating valence bonds. So the chemical bonding is changing. What do we mean by that? Well, a more modern picture would be to replace the double arrow by a plus sign. This is really exactly a quantum superposition of two different bonding patterns in the molecule. Okay. And the chemical bond is actually exactly an EPR pair of electrons, just as I described. That's what a chemical bond is. So this is a simple example within a molecule of an entangled structure. It's not really long range, entangled very far apart, because a benzene molecule is still incredibly small. In 1973, Phil Anderson, who's one of the towering figures in theoretical physics, suggested a generalization of Pauling's idea of resonating bonds in chemistry to spins, electrons in a solid. He suggested that localized electrons in a solid like this might undergo this kind of resonance. And he called this a resonating valence bond, or RVB state. He also referred to it as a quantum liquid of spins. Because of this name, we sometimes call these things now quantum spin liquids. I've only drawn two components to this wave function. But what you should have in mind is that this is a sum of all possible ways of placing these little valence bonds on this lattice. So there are many, many terms, much more than I could possibly ever draw. I told you that anytime we add states in quantum mechanics, we can multiply each one by its own amplitude. So to really specify this state, to ask what's the information in Anderson's RVB state, we have to give a number for every one of these terms that we could write. And there's so many of them. If you were to try to actually write this state down for 500 spins, there would be more numbers, more amplitudes in this wave function than there are atoms in the visible universe. So there's an incredible amount of information, incomprehensibly large amount of information in this type of highly entangled state. So this is very, very complex entanglement. This is a kind of possible entangled state of a macroscopic chunk of material, actually a magnetic insulator. The question we can have, though, is it robust? Is this complex braiding pattern going to fall apart? So this is where the subject of this summer's school comes in. This is a poster for this summer's Boulder School on topological phases of quantum matter. Topology enters to provide some robustness. So what is topology? Topology is not physics, it's mathematics. But physics has a habit of taking mathematics and using it. Topology is a study of which objects can or cannot be smoothly deformed into one another. So for example, as shown in the picture, a donut has the same topology as a coffee cup. You can smoothly deform them one into the other, but it has a different topology than a sphere. In the past decade, it's become clear that topology has enormous applications to physics, and our students in the summer school are learning all about that. In physics, we like to quantify why it is one object can't be deformed into another. What's topologically different about them? That is called a topological invariant. In this case, it's something called a genus, for a surface like this. It's basically just a number of holes. Okay. So the donut has a hole in it, and a sphere doesn't have a hole in it. That's why they're topologically distinct. So these ideas of topology apply to quantum states as well. That's the realization which has been leading to at least part of this revolution I was talking about. So here's an example using that RBB state I showed you before. I'm showing, instead of writing the sum of components in this state, I'm drawing it as an animation. These valence bonds are moving around in different patterns. You should think about the real quantum state as a sum of these different pictures. Now, as you look at this picture, I want you to notice at any given instant how many of these valence bonds are crossing this black line that I drew. At some instant there's 1, at some other instant there's 3. At different times you see 1 and 3. There'd be other numbers if we looked at a longer sample. But what you notice as this happens is the number is always odd. It turns out that the oddness or evenness of the number of valence bonds crossing this line is an example of a topological invariant. Because this is a quantum state, we can store quantum information in these topological invariants. That information is not anywhere local. You need to know the parity, oddness or evenness of the number of valence bonds crossing that line. I have to be able to look at a whole line in space. So it's distributed globally over the system. So with topology behind you, you're protected. Topological protection can prevent decoherence or errors in storing this quantum state. Now, if you start thinking about coffee cups and donuts and spheres, start thinking about what type of objects can be transformed into one another, you might think of a very familiar example, which is knots. It's very easy to end up knotting a rope if you're not careful. And in fact, there are many, many, many different types of knots. Okay. Even a simple thing like a rope can have a huge number of different possible topologies, states that cannot be transformed into one another. So this applies, in many cases, it applies to quantum states as well. It turns out there are many, many possible different types of entangled quantum states. So each one of these different types of entangled quantum states is something that can't be transformed into another one. It's a different quantum phase of matter. I already showed you classical phases are very rich. Quantum phases are even richer. When you learned that there are only 3 phases of matter, you were lied to. There are many, many, many more. And even more when we think about these new revolutionary quantum states of matter. So that's pretty cool, right? We think we can maybe make matter that is just very different from the stuff you're used to. What does this strange stuff look like? Kind of in my mind, I imagine something like this. I don't know. It's glowing, maybe. It's something very strange. But, okay, it doesn't look quite that cool. Here's some examples. The top one is a naturally occurring mineral. It's called Herbert Smithite. It's named after like a geologist, Herbert Smith. It's a naturally occurring mineral discovered in Chile. If you produce very nice crystals of it in the laboratory, it looks like this, a kind of light green-blue color, semi-transparent. Here's a new one, another material, like terbium magnesium gallium 04, which was just synthesized last year. It's also semi-transparent. They're both crystals. The bottom one is bismuth selenide. It's a semiconductor, kind of shiny semiconductor. It's actually already used as a thermoelectric, something which can convert temperature gradients into electric power, or vice versa. When you look at these things, you don't see anything especially quantum about them. So quantumness is not so obvious. So if it's not obvious, how do you detect it? And if it's hard to see, is it actually good for anything? So these are kind of questions that physicists are working on. They're working on how to observe and use the weirdness of this type of quantum matter. So we're not sure we know all the ways of possibly observing and using it, but one thing we do know already is that this strange stuff behaves as though it has strange particles in it. So we know what the matter around us is made of. It's made of electrons and protons and neutrons, and there may be some photons flying around. So that's basically everything that you ever encounter in your life is made of that stuff. Nevertheless, inside these strange quantum materials, the world behaves as though there are different particles, strange particles, that are different from the particles of our world is actually made of. These are things we call quasiparticles. So let me try and explain that by analogy. Quasiparticles are something that can be produced inside this complex quantum state. We can think about this complex quantum state with its pattern of entanglement as some kind of complex mosaic, like some pattern that you might observe in some cathedral, some Islamic tile pattern or something like that. So like any, but this is a quantum texture, a quantum pattern. So like any regular pattern, it can be interrupted somewhere. There can be some mistake in the pattern. If you don't have a good tile guy making your bathroom, you might misorient those tiles somewhere and make what physicists call a topological defect. Well, you're actually intimately familiar with topological defects. If you look at your hands, you'll all see them on your fingers. Your fingerprints form layered ridges, where the ridges are kind of locally parallel to one another. It's very similar to the patterns formed by some liquid crystals that actually make up the displays in your iPhone or probably your TV, for example. What makes everyone's fingerprints unique, actually, though, is the pattern of topological defects. If you look at the center of this finger, there's an example of one, which is usually called disclination. I'm sure it has a name in fingerprinting. That's a topological defect. Anytime there's a regular pattern like this, topological defects will be present. For a quantum wave function, they form kind of, if you want, unique fingerprint of that quantum state. But that topological defect, it can move around and it actually behaves like a new type of particle. That's the quasiparticle. Not an electron or a proton, but something new. And different quantum states, different patterns of entanglement will have different types of these quasiparticles. So for example, bismuth selenide, it's an example of what is now called a topological insulator. And it has a type of particle in it that is always stuck to the surface of the material. It never actually goes deep on the inside. It gets stuck on the surface, and it behaves for all the world like a massless neutrino. And we now know, physics aficionados probably know that neutrinos actually have mass, but for a long time we weren't sure. We thought they were kind of almost, they're a massless version of electrons. But this thing really is massless, and its masslessness can be measured by various fancy techniques. This is a picture produced from something called angle result photo emission, which is a way to measure this funny particle. These other two crystals I showed you before, they're realizations of Anderson's dream of spin liquids from more than 40 years ago. Deep inside this crystal, we imagine some pattern of entanglement. Sorry, no movie here. I ran out of time to produce the animation. We can have a defect which behaves like a particle, which we call a spin-on. A spin-on behaves a lot like an electron. It has the same spin as an electron, except it has no charge. It's electrically neutral. We're not sure what the applications of these strange quantum spin liquid states are, but we can imagine using these weird neutral spin-ons. They are probably the beginning of a new class of materials that can conduct heat like metals but are electrically insulating, and which could be strongly sensitive to magnetic fields, might have applications as sensors, non-conducting, thermally conducting but electrically insulating materials must have many uses. There's even more exotic examples of quantum matter that can have quasiparticles that are something called anyons. An anyon is a very funny thing. If you take an anyon and you move it around another anyon, something weird happens. The amplitudes in the entangled superposition of the state actually change. So remember, those amplitudes are the information in the quantum state. So if you can manipulate those amplitudes, you are changing the information in the quantum state. And so you can actually perform a computation using those, by changing those amplitudes. So Alexei Kitaev, one of the geniuses in our field, came up with the idea that we could actually use these anyons by moving one around another to actually perform a computation, perform a quantum computation. In this picture, this is a picture drawing what we usually in physics call world lines of particles. You can imagine the vertical direction is the time direction, and in the horizontal direction we're showing the position, and it's a kind of pseudo 3D view. You can see where these particles pass under or above each other. You can, from this, reconstruct motion of these particles in a two-dimensional plane as a function of time, and you're kind of winding one particle around another in some complicated way. You can see it looks like kind of braiding together some strings. Okay? It's a bit like knitting. So the future may be very weird. It may very well be that the future quantum computers will, when you program them, programming might be more like knitting. So up to now I talked about kind of practical applications. In physics, we always like to also think of intellectual applications and ask, can we use these ideas, concepts developed to understand kind of familiar matter that we can get our hands on, things in our real world that we can make in the laboratory, can we use them to understand fundamental physics, the kind of physics that we might probe at a giant particle accelerator like the LHC, or a gravity wave detector like LIGO? So we can ask a question, a very provocative question: can the elementary particles and forces of our world actually emerge from entanglement? So let me give an example of electromagnetism. Electromagnetism is a phenomena, that's been known since ancient times. Both Chinese and ancient Greeks constructed compasses. They knew about magnetic forces. They knew about static electricity. In the 18th century, Charles Augustin de Coulomb discovered the law governing the forces between electric charges and between magnetic poles. At that point, we had an understanding of static electricity and static magnetism, but there was no real understanding that they were related. In 1861, what was a huge impact in physics was the work of James Clerk Maxwell, who gave a complete classical description of electromagnetism. He developed what are known as Maxwell's equations. They describe electricity, magnetism, and their combination, both statically and dynamically, And what Maxwell found, most amazingly, is when he wrote down the equations that describe electricity and magnetism, electric and magnetic forces, the solution of those equations jumped out and told him that there must exist a wave, something that propagates and moves at the speed, at a certain speed, which turns out to be the speed of light. What Maxwell discovered is that light is a wave, and light itself is a form of electromagnetism. That was in 1861. Not that long after, 44 years after, Einstein wrote an amazing paper on the photoelectric effect. So the photoelectric effect is the effect that if you shine light at a surface of certain materials, usually semiconductors, electrical charges, electrons will come off. But this is actually the basic effect that is used to produce photovoltaic solar cells, okay, solar panels. What Einstein explained in 1905 was that characteristics of these experiments proved that light is actually made up of particles called photons. They didn't behave like a wave. This is probably something you heard about in quantum mechanics. Is light a wave or is it a particle? Which one is it? Well, this is one explanation. But quantum mechanics actually explains it. Light can behave both as a particle and a wave, and the reason is because of quantum superposition. You can think about the electromagnetic wave as a superposition of light particles, photons, just in different positions. That's what the wave is. It's a kind of amplitude wave, often called probability wave of a photon. So all this theory by now, including work a little later than the photoelectric effect, has given us a complete quantum theory of electromagnetism. There's nothing we don't know how to model in electromagnetism. Okay. Except one thing we don't know. We don't know why electromagnetism exists. We can describe it completely, but we don't know where it comes from. Weirdly, some understanding of where electromagnetism might come from comes to us now from understanding these highly quantum states of materials. So inspiration can come from strange directions. This is Mike. You saw him earlier here. He's one of the faculty in physics here. He showed back in his thesis that the full physics of electromagnetism could emerge from something completely different, from entangled quantum spins on a particular type of lattice. It's called a Pyroglor lattice. This is a little model, plastic model of it. And to do that, he used the kind of ideas I discussed. One of the students in our school here, Lucille Savarine, a little more recently demonstrated that this, which was just a theoretical idea, may actually apply to some real materials. Well, this is a grown crystal of one of these things, terbium titanate. And we believe that if we find exactly the right material and cool it down to low enough temperature, it should behave as though electromagnetism, the full glory of electromagnetism, has emerged inside it. These are materials called quantum spin ice. So inside this strange quantum stuff, nature is creating a new form of light and electromagnetism all over again. So it's an open question. We now understand at least one way in which light and electromagnetism can actually emerge, where it can come from. But what we don't know if this is the way light actually emerges in the real world. That's an open question. So the most challenging force to understand in nature is gravity. It's a huge problem. People have worked on it since Einstein's revolutionary work himself. The main difficulty is that, unlike for electromagnetism, there is no quantum theory of gravity. Okay, this is actually a slide taken from a talk by Mark von Ramskamp, who's someone who works on the problem of quantum gravity. Last year at my institution, where he shows gravity as a square peg in a round hole. It's very difficult to combine gravity with quantum mechanics. So it's different from electromagnetism. We have a complete quantum theory of electromagnetism. We just have to determine where it comes from. We don't even have a theory of quantum gravity. So if we want to know where it comes from, things are more challenging. Another reason why it would be very hard to figure out where quantum gravity comes from is that what Einstein taught us about gravity, that's his theory of general relativity, is that gravity shouldn't really be thought of as a force. We should think about gravity as really the structure of space-time itself. So if we want to explain where gravity comes from, we really are trying to explain where does space-time come from. So that is obviously a pretty deep question. Not easy. Still, if a rock could inspire us to explain the origins of light, maybe something else in the material world could inspire us to have some idea of the foundation of gravity. And it may seem far-fetched, but recently there's something, an idea is really coming that might give it a hint at least at where gravity comes from. And it comes from something very humble. It comes from a theory that would apply to what we would call a quantum dot. A quantum dot is just a small piece, a little tiny chunk of some material, usually a metal or a semiconductor, that holds some electrons in it. So the quantum dot might tell us something about gravity. So last year, Kataya, I've already mentioned him before, he's a kind of a multi-talented genius, suggested that a particular system of electrons that exert strong forces on another, these dots are supposed to be electrons, and the lines are these different forces. You can imagine them living inside of this little quantum dot, which is, you should think about it as a tiny grain of a superconductor, a little piece of superconductor. A strongly interacting enough tiny grain of superconductor might actually lead to gravity. And here he is showing the structure of space-time for this emerging out of this quantum bubble. Now I have to confess this is not gravity in our world. This is a different version of gravity, which generally is believed to be easier to find. It's what's called two-dimensional anti-de Sitter space. Has the wrong number of dimensions for our world, and it's the wrong shape of space-time. But it's still a pretty amazing step to get to from starting by thinking about a little chunk of metal. And these ideas are being extremely actively pursued to see if they might actually lead somewhere closer to reality. I see I'm going pretty fast. I'm actually about done, so I think nobody ever complains about a short talk. So let me leave you with a quote from Niels Bohr, or a couple quotes from Niels Bohr, one of the founders of quantum mechanics. He has a lot of amazing quotes, actually. Everything we call real is made of things that cannot be regarded as real. I tried to convince you of that. And if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Unfortunately, it's possible to be shocked and still not understand it. Thanks.
Well, Leon left us plenty of time for questions, so I welcome questions from the audience. Yeah, go ahead.
Is there as an engineering field, that there was also a lot related to the surface, the shape of the surface, the giant edges, the roughness of the surface as well?
Indeed, so the coefficient of the area might depend on the shape of the surface. That's not understood all that well. It's understood in some instances, but it indeed is right. So there's some notion of how to, if you want, so there's a classic problem in classical physics which is called measuring the shape of a drum. If you can understand the sounds, the different frequencies produced by a drum, can you deduce the shape of a drum? Maybe by understanding the pattern of entanglement, you can determine the shape of this region whose entanglement you're measuring. It's an interesting question, not fully understood. Sorry?
You stun because it's silence.
Stunned you into silence.
So this is like super unscientific probably, but do you remember the book A Revolution, Thomas Kuhn?
It's a famous book. I actually haven't read it, but it's The Structure of Scientific Revolution.
Yeah, and so, I mean, I had like this much physics, go Gauchos.
Go Gauchos, right?
But it seems like what I'm hearing in my very limited knowledge is that, and in reading a little bit of that book, is that, you know, he put forth that basically we need a paradigm shift. And what I'm hearing a lot of is, you know, you're still trying to quantify, and you still say, well, we have to make it conform to, to reality, when maybe it's the other way around. Like, you know what I'm saying? Like, we're still trying to fit it in to this structure.
Well, we're trying to understand what reality is to some extent.
But we kind of think we know. It's kind of what we see in front of us.
Well, that's what quantum mechanics tells us, that,
No,
that what we
exactly.
see in front of us is not
I
really
think
real.
that's what I think what I'm hearing, and like I said, from the little I've read, or actually the lot I've read, it seems like we keep trying to fit it into, kind of a restricted paradigm when it's telling us that's not how you look at it. We do that with everything, especially in Western culture. And so I'm just wondering, I don't know how we get there really, but I'm just wondering if it's our way of looking at it. Because it doesn't fit reality because it's not our sense of reality.
Well, we're limited by our senses, of course, but to speak a little bit to this question of scientific revolution, I think there's a lot of evidence that we are in the midst of a revolution related to our understanding of the quantum world. And part of it is coming from a convergence of different fields. Now, I come from theoretical physics, but there's an entirely separate group of people who come from computer science and who have discovered quantum mechanics and are investigating questions of information in quantum mechanics. And bringing these two groups of people together is what is really galvanizing all this progress right now. I think that's a sign when fields converge or new fields are created. That's what's going on now.
Yeah, thoughts are emerging and expanding, it seems like.
There's someone back there with the hat.
I just hired a little anyway, why wouldn't all this be easier if we thought, as some people claim to think, that space, dynamical configurations of space itself, and indeed the vortices in space, are good ways to think things apart. In other words, that, well, in science, of course, we said a particle is a whole of a theory, and if the topology of the dynamic topology of a fluidic model of what's going on, where we thought of it, seems to me, well, other things fall out in the map as far as what is going on.
Well, so I think you make a great point. In fact, certainly we expect that an eventual theory that will describe quantum gravity and everything else will, in that theory, space-time will be dynamical. And moreover, we're struggling to find the relations in this new way of thinking between particles, quantum information, and space-time. Something I didn't mention, but is part of this general discussion of entanglement and its relation to space-time and gravity, is an idea that an EPR pair may be actually related to an idea in a concept in general relativity called Einstein-Rosen bridge, ER. So it's a very cute name, EPR equals ER. There's a lot of speculation and a lot of very interesting theoretical ideas that entanglement and gravity are almost two sides of the same thing. And entangled particles may themselves have something to do with changes in the geometry of space-time.
But if we think of particles as vortices, just by playing that language game, there's actually an unfolding possible theory.
I'm sure there are lots of ideas to pursue in physics. We need to explore many of them and try to see which ones we can make quantitative. If my friend Matthew Fisher, who's another one of the founders of the Boulder School, were here, I'm sure he would love to. He's a big fan of thinking of everything in terms of vortices. Discuss with him. Sorry, there was another person here first. Maybe I can come to you next. In the blue there. Yeah.
So we were talking about like the errors in the, I don't remember what it's called, but I'll say the spin-ons were actually just like where a bond or something wasn't what should be, so that and then you talked about anyons after that. Are anyons like the same kind of thing?
Anyons are, so they're another sort of topological defect, if you want to think about that, in a quantum state, in a quantum pattern or weave. Just a more complicated one that I can't draw quite as simple a picture for, but yes.
So do you think there's any connection between topological invariance caused by entanglements and our conservation laws, conservation of energy, for example?
Well, energy is a particularly tough one, but certainly so it's possible to, there are certainly theoretical ideas that explain some conservation laws, like conservation of charge, conservation of flux, these kind of things. These can arise out of topological conservation laws. So this is an idea heavily pursued in theoretical physics, and it's integral to another theoretical concept, something called dualities. In duality, there can be two very different theoretical descriptions of the same phenomena. And in one description, a conservation law is a regular conservation law. In another one, the conservation law is topological. It's just a topological invariant. So there are actually many examples of that in theoretical physics. Just speak up. Oh, way out there. Okay.
Yeah. Question for you. Maybe you're related or not. Breaker spin in classical physics, I'm thinking of the old bicycle wheel experiment where it's spinning and then you push it, it goes in a different direction. Is there any relationship of that at the macro level to something going on down here?
There is. So there are both examples of angular momentum.
Right.
And an electron spin is a quantized version of that macroscopic phenomena. At least it mathematically behaves in a very similar way. It has certain quantum peculiarities to it that are different, that are really the result of quantum mechanics, uncertainty principle, things like that. But it's not dissimilar. So when I drew a picture of an electron kind of rotating, it wasn't entirely a lie. It wasn't entirely false. That's a picture that physicists have for spin.
Sure. Stuff going in different directions. The force of that.
Yeah. You can apply a torque to that spin.
I know that there's like a general theme in physics to find, the theory of everything. And my question isn't very technical, but so I was wondering when you were mentioning how we're starting to understand gravity through quantum mechanics. And do you think, so my question is, do you think that quantum mechanics might be the first step towards finding the theory of everything and that's starting to explain lots of a broad sense of things?
Well, it would be very bold for me to make any strong statements. People have been trying to find the theory of anything since the time of Einstein's time and earlier, and very concrete progress on the problem of. So we have a theory of everything except gravity, first of all. Okay. The last step of understanding gravity is much harder. Now this is an example of some promising progress, but it's purely theoretical progress, so it's possible that it's not in the right direction. But I think it's very promising. And in this point of view, gravity may be something that really comes out of quantum mechanics. I don't know. I think the prevailing, probably more conventional view is probably that quantum mechanics and gravity both come out of something else, which is different. There's someone up there.
I was just wondering if you could expand a little bit more on how you can find gravity within the quantum dot.
That's hard.
Couldn't hear the question.
She wanted to ask, can I explain a little bit more about how you can find gravity within a little quantum dot? Okay, so a quantum dot is a very small object. We want to think about the size of it being very tiny, and so it's essentially, physicists would call it a zero-dimensional object. Okay? But there's one dimension, of course, which is time. So the gravity which emerges is a theory of gravity not in just one time dimension, but one space and one time dimension. So the weird thing that has to emerge out of it is this space dimension, which isn't actually present in the dot. Okay, so that's the most amazing thing. Any theory of quantum gravity has to be like this. A dimension has to emerge from somewhere. Where does it emerge? It emerges from energy somehow. That there's in this kind of strange quantum dot, there's a hierarchy of different energies that emerge, and these energies behave like an extra dimension. So I don't know if that helps, but that's... down here and then...
Yeah, will quantum mechanics be able to explain dark matter and dark energy in the future?
I'm not an astrophysicist. I don't know. I mean, most people believe that dark matter is likely to be some other particle that we haven't discovered. There are candidates out there. It's possible. Dark energy, not clear what dark energy is. It may just be dark energy can be explained by something called cosmological constant. I don't know. It's not my field. A good theory of everything will explain everything. You know, I'm a lowly, what we call condensed matter physicist. I work on rocks. I'm stretching myself a little bit to answer some of these questions. Gaia?
So the spin limit that you're referring to earlier, you kind of proposed as an alternative to other forms of long-distance quantum entanglement. Does that mean topological protection or protection from the unit photons and photons, unlike
yes. That's the idea. That's the idea. Exactly. That's why these type of quantum states that have some topological protection are appealing for storing and manipulating quantum information in some way. But they may have more mundane applications, like, as I was saying, a heat conductor.
So theoretically, then you could operate at room temperature and still kind of maintain quantum coherence?
Okay, that's a little bit different question. We have to understand the effects of temperature. Theoretically, in some materials, not the ones I showed you. Yeah.
Is there some speculation about dark matter being some form of condensed matter that started around early Big Bang?
I know there's one speculation that has to do with tiny black holes. So that's certainly very condensed, extremely dense. As I said, it's not really my field. Seems to me we don't understand very much about dark matter. It's rather speculative field.
Are you concerned at all about human limitations of testing future theory? Whether it be like limitations on energy or anything like that?
Of course, you know, that's a huge concern in experiments in elementary particle physics or in gravity wave detection. These are all huge experiments that take tens of billions of dollars and span decades. Okay.
But not even beyond money, just
yeah. No, one should be concerned, but on the other hand, so the world of experimental physics is extremely broad. You know, from my point of view, where I'm primarily focused on understanding states of matter, there's an infinite variety of these things. And it's not economically that difficult. Many labs can study these things at a moderate cost. What an interesting question is, are we limited by our experimental tools? This phenomenon like quantum entanglement is not something that we've learned to measure. And you know, when we look at those, I showed you these pictures of these very quantum materials somewhere here, and where were we? Here, and they look pretty ordinary, but it's because we're looking at them, you know, with a simple probe, which is our vision and optical light. You know, over the last decade, several decades, physicists have developed all sorts of new probes. Maybe we need to develop even new types of experiments to unveil this quantumness. I think that's part of the challenge of this field.
What was the
these materials that's different from other materials that produces these properties?
Great question. Yeah, that's one of the very hard questions. It's a big challenge to try and understand what are the essential ingredients to make a substance display this highly quantum behavior. Okay, so we understand certain, for example, we know pretty well how to predict which materials behave like this bismuth selenide, these topological insulators. We figured out computational techniques and understood the basic physics to be able to predict those materials very well. And consequently, we can do this using a little bit of intuitive understanding, but then checked by computational physics programs. The type of materials at the top is much more challenging, actually, and we work more by rules of thumb, and then going back and forth between experiment and theory. It's rather not such an informed search right now. If we knew how to do that, we would be in great. We'd be very, very happy.
So at a macroscopic scale, is there something akin to entanglement? That you could take something macroscopic and make a change in state, and on the other side of the planet, something entangled with that would change? That's also at a macroscopic scale?
So, that I think is, that really would be creating a Schrodinger cat. We would call a Schrodinger cat state, not with a cat, something else, okay? And as I said, that's what we call an exponentially difficult thing to do. So the more atoms or more photons or more electrons are in each one of those objects, the harder that becomes to produce. And the scaling of that is exponential with the number of those objects. So it becomes very, very difficult. I think we're not going to be able to do that. The quantumness of these materials is a somewhat different nature than that. We try to understand in what way it is. What can we do with
it? It's limited to the infinitely small scale.
So we can take a single pair of photons and entangle them very far away. The distance between them can be pretty big, but they need to be 1 photon. So that will grow, but that will grow very slowly. One of the things that people are trying to do is to build quantum computers out of spins or photons or other degrees of freedom like this. Scale up. Right now people can do maybe, 5 to 10 quantum bits. They're nearby to 1 million. It's been huge efforts to do that going on in labs all around the world.
Well, it's getting kind of late, so I suggest we thank Leon again for a great lecture. If you have more questions, come on down.